All right, so concept 0 is that diffraction is the spreading out of waves when they pass beyond a barrier. So if we've got like an opening like this, and we shine a laser light, and these are like the crests. You know, we shine a laser beam on it, and these are like the high electric field crests or something like that, right? The notion is that when it passes through this barrier, that it's going to spread out some amount, right? That there's some angle of spreading like that, and that's diffraction. And concept 1 is that small wavelengths don't spread out very much, but big ones do. Okay, so small wavelengths don't diffract much, and large ones do. Right. So as the wavelength goes up, the diffraction, the angle of spreading goes up. Right. Now, have you ever wondered? Because this is true for like speakers, right? Have you ever wondered how it is that you can take a subwoofer and put it behind a sofa, and it fills the whole room with sound, and that never bothers people? But if you stick the high frequency speakers, the little bitty speakers on the home stereo system behind the sofa, that really messes it up. Have you ever wondered that? Well, that's because the high frequency ones are very, very short little wavelengths. Those don't spread out to fill the room. They might ricochet around annoyingly, right, in the room, but they don't spread out, right? Whereas the large wavelength waves, those are the ones that spread out. Basically that subwoofer, and we're going to figure this out in a sec, right? That subwoofer, the opening of that thing, right? It basically spreads out from that opening and fills the whole room. And then you can just stick like a couple satellite speakers, like here and here, and that suffices to create all the stereo imaging and stuff in your head. Have you guys ever been to, I think it's Bose in Pioneer Courthouse Square? Yeah. Go down there and have them do a demo of their system for you. And what they do is you walk in there and they've got these ceiling to floor speakers, and they're like, honest to God, this big, and they're like, wow, this is going to be great. And then they start playing this video, and the sound is just incredible, right? And then halfway through the video they stop and they go, okay, here's what was making the sound, and they pull those speakers away. They're just fake speakers, they're hollow. They pull them away, and there's a box about this big making all that sound, and then there's a couple speakers, honest to God, that are like this big, making all that sound, right? Yeah, so subwoofer and then just like mid-range and tweeters, right, are just sitting right there. Okay, then they do, this is the most amazing thing, right? They take those speakers and they put one of them in a box, and it sounds like crap, right? It's just like boo, 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 right? And then they press a little button and say correct for the acoustic environment, and the thing does this like crazy Bose algorithm stuff, yeah, right? You know, and suddenly the speaker sounds like 95% as good as it did, right? They've just stuck the thing in a wooden box, and it just sits there and corrects the acoustics of that box, right? So presumably you can put it in a room that's not a perfect acoustic environment and go correct. It's got little microphones that go, okay, I'm putting this waveform out, but this is what I'm really hearing, and it corrects for that. Isn't that amazing? It also costs, a system start about $8,000 or so, right? But what it is it's like a whole room sound. It's like your whole house sound system. You take your CDs and DVDs and stuff and stick them on a huge hard drive, and then you can like pull up, you know, music that you want in every room and stuff like that, right? It's like, there you go. I know. It's probably worth $8,000 or more, but it's, you know, there we have it. We just don't have $8. Okay. That's what you can buy with $2,000. Okay, so here is our formula. Oh, here's another example of this. Suppose you have a boomer car going by. Have you ever noticed that you hear the boom, 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 right? Don't you hear that for blocks and blocks and blocks as the car approaches? But as the car goes by you and the windows open, there's this brief period where you hear the all the high frequencies in the song, you know what I'm talking about, right? Just listen for that next time, right? The subwoofer, the bass notes are coming out through whatever windows open in their car, spreading, filling the neighborhood, and it's a good thing too, right? You know, and then the high frequency is basically line of sight. So as soon as it's like a beam of light shining out of the car, right? As soon as you're standing there. As soon as the car goes by you, you hear it. As soon as they go past, you only hear the bass again, right? Okay. This is the formula in your data packet. That's an equal sign. I always thought it was like approximately equal, but this is the wavelength here, right? So that angle there, that theta, okay, is approximately equal to the wavelength divided by B. This is B here. Okay? B is this dimension. That's the aperture. Is that how you spell aperture? I think I said size of opening because I wasn't sure how to spell aperture on the PowerPoint, right? Okay, this is the wavelength. And so we can do a little calculation here. Okay, 656 nanometer light, that's like reddish light, is incident on a single slit with a width of 0.12 millimeters. What is the approximate width of spread behind the slit? Well, 656 times 10 to the minus 9th meters is the wavelength. So nano is 10 to the minus 9th, right? So 10 to the minus 9th nanos is nano, right? Yeah. Okay. And then the slit, that's the lambda, right? And then 0.12 times 10 to the minus 3rd meters, that's B. And now we can divide them, right? 656 E minus 9 divided by 0.12 E minus 3. So on the millimeters, right? Just whatever they give you for millimeters, that's milli just means 10 to the minus 3rd. And then we can calculate this. And I'm getting a really small number, 5.46 repeating, right, times 10 to the minus 3rd radians, right? Yeah. How many degrees is that? How would we do that? How about divided by 2 pi times 360? Is that right? That's like 0.31 of a degree, right? Obviously, this answer is going to be in radians. Anytime you divide number by number, right? The thing you get is radians. Try that one. Sound waves with a frequency of 256 hertz come through a doorway that's 0.92 meters wide. That's like that doorway, right? 256 hertz is like middle C. What's middle C? Somebody sing middle C. Dum, dum. That was a whole step off. There we go. Right? So do you have to calculate the wavelength? Is that the first thing? Yeah, so to do this one, you're going to use, you have to use V as F lambda, find lambda, right? And then the second formula is you're going to go, theta is lambda over B, and B is 0.92. I don't know what units I've got it in. Okay.
Lambda.
Wavelength is bigger than a meter. Yeah, I get like 1.34 meters roughly.
I get actually 1.3398437.
See, I think I can divide by pi and multiply by 180. 83 degrees.
How do you determine the degrees?
Oh, let's see. Radians times 2 divided by 2 pi gives you like parts of the circle, right? Times 360. Because a whole circle in radians would be 2 pi radians, right? Obviously, you can divide by pi and multiply by 180 too. That also works, right?
Looks like you divide that answer by 2 pi and times 360.
Yeah, that works. So the wavelength I get is 1.3398, right? And then 1.3398 divided by 0.92 is that, which is about. So that means that the sound, if we had that sound out here in the room, right? Somebody's standing out here